question is no longer if, but when. Looking for life beyond Earth has been a human obsession for centuries, but it was brought into sharp relief not by scientists, but by creative spirits more than 100 years ago. H.G. Wells became a household name with imaginative works like The Time Machine and especially The War of the Worlds. French pioneering filmmaker Georges Méliès took things a stage further in 1902 with his hugely popular fantasy Voyage dans la Lune, or A Trip to the Moon. Wells was by no means the first to suggest alien eyes are upon us. Some of his predecessors were, after all, burned alive for even suggesting the possibility of life on other planets. But Wells's sustained invention was the game changer. The radio play based on his work caused widespread panic in the USA when listeners mistook what they heard for an actual alert. Two-time British Prime Minister Sir Winston Churchill, a Nobel Prize-winning man of words, penned an article in 1939 whose title was, "Are We Alone in the Universe?" "I, for one," wrote Churchill, "am not so immensely impressed by the success we are making of our civilization here that I am prepared to think we are the only spot in this immense universe which contains living, thinking creatures." Film and then television milked the idea of aliens for decades. Alas, it all amounts to nothing except a billion-dollar entertainment industry. What if, instead of waiting for aliens to come to us, we went in search of life beyond the world we know? Science is overtaking those visions. We keep looking, and we're getting better at it. Science and fiction are about to meet in the middle, when, not if, we come across life beyond Earth. We have only one reference point, our planet and the life on it. The complex DNA-based carbon life form that has infiltrated every nook and cranny of the environment on this planet, including its most hostile places. Volcanic vents on its ocean beds, its highest mountains, and its coldest regions. The assumption that organic compounds might be difficult to find in the cold, dark vastness of space is quite wrong. Space is full of them. As we have discovered in our exploration of our solar system, asteroids, comets, and meteorites do indeed carry the carbon compounds needed for life.
We discovered that this carbon was actually a very complex material, very complex carbon, very different from the simple molecules that we would expect to find there. So we don't see amino acids or alcohol or this kind of molecules which is observed in the gas, but we see something much more complex and very rich in carbon and poor in nitrogen or hydrogen compared to these other materials.
It appears the fundamental assets to make life are distributed throughout the solar system, a function of the evolution of planets. What at first glance appears a simple question, where can life be, rapidly spirals into a complex conundrum. The complexity of DNA here on Earth, and what other environments could facilitate such growth in complexity. Can biological life even get started in the harsh conditions of the solar system? Until concrete evidence is available, the question is polarizing.
I can't say for sure because we've only got the one example of life on Earth to work with so far, but all the ingredients are out there. Solar systems make everything you need for life, insofar as we know. So it could be that matter naturally organizes itself into life.
My answer to the question of whether there's life out there in the universe is, I'm afraid, I don't know. The great thing about being a scientist and not a politician is that I'm not required to have an opinion on anything. I'm only required to be able to tell you what the facts tell us. And what the evidence is that we don't know. We don't know how life on Earth got started in detail. We don't know how long it took. We don't know what the preconditions were. And so life could be incredibly common, because there are lots of planets out there, or it could be an incredibly rare event that only happens, on 1 in a billion planets in a galaxy.
You want to have fluids available. So water, insofar as we know, is necessary. It's necessary for biogeochemistry on Earth. So you would expect that anywhere where you have liquid water or liquid organics would be good places to look for life.
Another question for scientists. The environment that hosts life now may not be the originating location for that life.
Life now occupies almost every imaginable niche. Most rainstorms are seeded on bacteria that float around in the water vapor, and then they start to nucleate water droplets and down they come. So, life is just everywhere. And it's in Antarctic ice caps and in snow patches. And so it's everywhere at the moment, and it can survive for unbelievably long periods under harsh conditions. But are those the conditions you need to make life? Those are kind of two steps we've got to almost detach our minds from in two different kind of views. So that whole idea about, where do you start life? Because the most primitive organism is already an unbelievably complex piece of machinery. It's got a membrane that isolates an interior component that's different chemistry from the outside. It's got a mechanism for mobility. It's got this incredibly complex molecule inside. So those are almost like different pieces of a puzzle put together into something that works and can then self-replicate and such. So, even before you get to that stage, you have this immense series of events that we can't even really begin to understand yet. We're starting to, but how do you get to that stage? So you almost have to detach yourself from life, where can it live now, to the building blocks of life.
Life as we know it is a complex mechanism, capable of self-replication and great diversity. But what actually is it? How do you go from a puddle of organic chemical broth exposed to some form of energy and turn into this? To know how life evolves from the fundamental organics to functioning single-cell organisms is a key to the riddle of our times. To find answers in space, we must first look back at ourselves.
One of the really key questions to ask, first of all, is actually what is life? And biologists, as well as other scientists, actually regularly debate this, what actually is life. But in my own definition, it is basically these self-contained systems where basically they are taking up energy constantly from the external environment and then using this energy to generate biomass, and this results in growth and eventually replication. One of the things that's massively debated is whether the precursors to these molecules, such as amino acids and nucleic acids, were already available on Earth before life evolved. And one really popular hypothesis is that they were, and that with the help of electricity from lightning, fundamental chemicals such as carbon, nitrogen, and oxygen were able to react to form the first amino acids, which then form precursors to proteins, and also the first nucleic acids, which formed precursors to DNA. But my own hypothesis, and this is backed up by a number of other evolutionary biologists, is that these compounds were probably not that common in before life evolved, and instead it was life itself that started to create these compounds. And instead, they basically used pre-existing energy sources in the environment, with hydrogen probably being the key one here, to fix carbon dioxide, and then use this to make organic carbon. And increasingly you would have had more sophistication developed, where you would have formed the initial amino acids, which would have then gradually elongated, becoming the first proteins, and increasingly more complex chemical catalysis would have developed. In terms of life outside Earth, it's hotly debated whether this would be dependent on the same exact building blocks, but would almost certainly also depend on organic carbon, because carbon is such a flexible molecule and also such a stable molecule where it can polymerize, and it's by having these polymers available that life is able to conduct these complex chemical reactions required to basically convert energy into usable biomass. And so by focusing on energy as this sort of universal currency for life, it then becomes more possible to predict possible environments where life could be found and where life might be able to evolve. For higher life such as ourselves, we currently are highly metabolically inflexible, so we depend on organic compounds as our energy sources, and we depend on oxygen to basically combust these energy sources and generate usable chemical energy from it. However, in the case of microorganisms, they're basically capable of an almost infinite number of perturbations upon these processes. So while some microorganisms can use organic carbon, others instead use inorganic energy sources such as hydrogen, or alternatively they might use sulfur, methane, petroleum, iron, uranium. All of these microbes have been characterized on Earth, and we basically have something that we say in my lab, which is that if there is an energy source available, you can bet that there's a microbe out there that's able to use it.
One of the first places to look for the ingredients of life is in the remnants from the early manufacture of the solar system, meteorites.
We've discovered a variety of nucleobases and nucleobase analogs in meteorites. And so what a nucleobase is the small molecule that are the building blocks of your RNA and DNA, and these molecules are essential for all of life. So this has implications for the origin of life on Earth. We know that meteorites contain amino acids, which are the building blocks of your proteins, and now from our research, we can show that nucleobases, which are the building blocks of your genetic material, like DNA and RNA, are also found in meteorites. And so these things together could have seeded an early Earth with these really important molecules that could have built up to the larger molecules you see today that are essential for biology.
Meteorites do have potential for astrobiological exploration. One thing that my group's been looking at is because they fall to planets and moons in our solar system and are sterile when they do that, and they're actually pretty delicious for microorganisms. They have a lot of available, phosphorus, which is essential for all life as we know it, sulfur, carbon, organic matter. It's not a bad place to live. And we know a lot about meteorites. They're the best studied rocks in the solar system. So you can pick one up on any, like a stony meteorite from the early days of our solar system, pick it up on any planet or moon in our solar system and know basically everything about it. So you could tell, based on our knowledge of life on Earth, whether something had been living in it and leaving behind something that we call a biomarker, a sign left behind by life.
During the violent early lives of the planets, collisions and volcanic eruptions often blasted debris into space. One such rock was cast off from Mars 17 million years ago and fell to Earth roughly 13,000 years later. It contained some contentious signs.
So there's a very controversial meteorite, the Allen Hills meteorite. In the mid-90s, there were some studies released that put forward the idea that they might have contained nanobacteria from Mars. So the Allen Hills meteorite is a Martian meteorite, so part of the crust, the surface rocks on Mars. And it would have been ejected from that surface and fallen to Earth at some point in the past. And there were morphological features that looked like microfossils. However, the results are still ambiguous. It's really difficult to determine whether a textural feature like a microfossil is true evidence of a biological process, of the presence of cells. So typically we want to use microfossils, so textural evidence, an imprint of the cells or life that were in a meteorite or in a rock from another planet or moon. So we want to look for fossils and chemical evidence in terms of organics and inorganic chemistry.
Scientists need to go back and look at the only sources of evidence for early life: fossils.
Astrobiologists are mostly concerned with microfossils, so fossilization of single-celled microorganisms or communities of them. And so you can get various conditions that will preserve microfossils, but generally the common theme is that you need to replace them or preserve them with a mineral. In some cases, you can get microorganisms that change the chemistry around them, so pH, what ions are building up around them in a solution, and just as a function of the waste products that they produce, they can end up precipitating minerals. So crystals will actually grow on them or inside the cells, and eventually preserve a record of the microorganism having been there. And you can get, say, sulfide minerals like pyrite or fool's gold. Can preserve fossils that way, and also carbonate minerals are very good at preserving a record of microorganisms as fossils.
Recent discoveries of fossilized microbes called stromatolites in Greenland are helping pinpoint the earliest evolution of life. The time window is narrowing, allowing for more accurate searches elsewhere in the solar system.
Yeah, well, it's an extraordinary discovery in really two different ways. One is that these stromatolites are preserved at all in rocks that are 3.7 billion years old. We're just talking incredibly ancient periods of time. And the exciting thing is, and we put this in the title of the paper, that we talk about a rapid emergence of life. So these rocks in Greenland are actually almost the oldest preserved rocks in the world, of anything. And they're preserved in the immediate aftermath of what's known as the late heavy meteorite bombardment, which we know about from studies on the moon, was an intensive period of large bolides coming in and really impacting the Earth with incredible energy. In fact, enough energy that the oceans would have vaporized and had to recondense again, up till the period about 3.9, 3.8 billion years ago. So the thing that it's starting to point to is that, if life got started really early on Earth, and maybe it did, maybe back to 4.2 billion years ago when we know there were liquid oceans, it's hard to imagine it surviving through those incredibly energetic impact events until about 3.9, 3.8, and then we've got evidence of stromatolites at 3.7. So it's all about like, how long do you need to make life? That chemical soup, that energy to generate complexity, we always thought it took like 500 million or 1 billion years, but these discoveries are just shortening that time frame down to like 100 million years, which sounds like a lot to you and me, but actually on geological timescales, that's very short. And so it's really exciting in terms of thinking about what does that mean for generating life on other planets that don't have the long history of geology that Earth does. Like, we're still an active planet, but Mars, other planets have died because they're smaller. But then the question is, could they have formed life? Well, this foreshortened period suggests that, yeah, maybe they could. And that expands our envelope for thinking about where to search for life in the solar system, in the universe, really everywhere.
However, with these recent discoveries, a new theory is emerging into the spotlight.
At the moment, a developing paradigm shift in the community about where did life get started on the planet. So at the moment, it's known, or it's been theorized, that life started in the deep oceans by these hot vents that extrude mineralized water onto the sea floor, 400 degrees temperature, thousands of meters below the ocean's surface, no sunlight, just chemical energy. And that's been a really evocative model for a long time. But now, people are starting to see that there are problems with that model. And it's not about life living at those vents. We know that's the case. We can see it with our rovers when we go down. We see these big tube worms and crabs and everything. But before you get life, you have to make organic molecules become more complex. So organic molecules are simple, they're everywhere, they come in from meteorites and comets and dust falling in and stuff. But to make them complicated, to make them long chain, you've got to stick those bits together. And the funny thing is that sticking those bits together requires not just wetting, but drying conditions. Each of those reactions that makes an organic molecule longer requires a water molecule to be kicked out. So the community is starting to realize that actually you can't make life in the oceans. It's actually too wet. So we're now, and with a group of us, looking at hot springs, because hot springs on the surface of the Earth have all the conditions of the deep sea smokers. They're not as hot, so that's actually better. And they have the capacity for wetting and drying cycles on the edge of hot springs pools that have geysers, they erupt and they expand and they detract. And so you get these wetting, drying cycles. That provides the power and the energy for making complex organic molecules. And their chemistry is very complicated. Each hot spring is different. One's pH 2, one's pH 7, one's pH 11. They've got different nutrients, different chemicals. And you mix and match all those things together, and all of a sudden you've got complexity that could make life in something like 10 million years. So this is a new model that we've just published in Scientific American, very exciting, and it's applicable to Mars. Because it looks like from the history of the geology of Mars that actually it never had oceans. But it had volcanoes and it had hot springs. So if our ideas about the origin of life are changing from the deep oceans, where we'd say, why would you go to Mars? They never had deep oceans, so life wouldn't start there. To hot springs, all of a sudden Mars are going, very exciting.
The next obvious target for scientists is our age-old agent provocateur, Mars, the closest in time and space to our Earth, and the best first chance of evidence of non-terrestrial life.
Absolutely. We're looking at exactly the same window of time as the discoveries from Greenland through to our well-known work in the Pilbara in Western Australia, where there's the most convincing evidence of life. The whole community's satisfied about it. But that window, 3.8 to 3.5, is exactly the time in the history of Mars that we know it had warm and wet conditions, or at least wet conditions with abundant flowing water. And so that's exactly the window that we're looking at. And that's why these areas are so important as analogs, because they really are, a window back onto this incredibly deep time period, and at the same time on Mars, when things were still going on there. We still had volcanoes that were providing heat and volcanic activity and chemical complexity and water-rock interaction. Those are all the things, ingredients that we need for life on Earth, and we know that we had them on Mars. So that's why we're looking at these comparisons and going, that's the time and the place to look.
The next Mars rover mission, Rover 2020, is fast approaching. Scientists and technicians have one shot at finding ancient signs of life, so their landing site selection is a serious business.
We're literally on the advisory team for one of the landing sites for the Mars 2020. We've gone over the past 2 years to the landing site workshops where they're whittling down the numbers, and at the moment they're the top 3 sites candidate for the Mars 2020 mission, and ours is still one of them, and that's to go and look at what appear to be, from all the evidence we have, hot spring deposits. These silica-rich deposits from extruding hot water that's coming out of the ground and flowing over the landscape. And we're so excited about that because the work that we've done in the Pilbara has shown that at 3.5 billion years ago, the same age as the crust on Mars, this ancient life on Earth was thriving in active hot springs with geysers depositing opaline silica. And they found from one of the previous rover studies on Mars, the Spirit rover, found opaline silica deposits. And they've got textures. I mean, this is totally mind-blowing. They've got textures like these little fingers coming out of these silica things. So it's not just boring layered rock. These have vertical structures, finger-like structures, and they found identical structures in hot springs active today in these very high desert areas in Chile, the most Mars-like conditions you could ask for. Bang, we've got the same structures, opaline silica, these finger-like structures, and on Earth, they're made by microbes. So we're saying, go to those known hot spring deposits on Mars.
Another area of interest is the detection of methane gas in the atmosphere. More tantalizing clues of possible life processes.
I reckon that's geological. So there are geological processes that will produce organic molecules, including methane, including the process of serpentinization, which is when you have, essentially you heat up magnesium and iron-rich rocks and add water into them so you hydrate it. It's what we call a metamorphic reaction. And that can generate organic matter or organic chemicals. That's well known from studies on Earth. I really hope that we do find fossilized microorganisms on Mars. That would be a triumph for science and for humanity. I'm not holding my breath, though. It could be a long journey to try to find a record there, but it's probably our best hope in the solar system.
There is another consideration when looking for alien life, in particular on Mars: contamination. Earthly bacteria can easily ride the rocket through space and land on Mars with the probe, leaving the distinct possibility of contaminating and possibly destroying the very thing we are looking for.
Yeah, look, this is a real possibility. And there's a group in NASA, and I'm sure that other agencies have them as well, called Planetary Protection Officers, who take the most careful steps imaginable to try and protect the planet from seeding with our own sort of bacteria community that we bring in with us everywhere. And so that's the main reason why the Mars 2020 mission is not going to look for active, like existing life, because we know there's water flowing on Mars. It's coming out from the subsurface, but we know that can live on Earth, no problem. But they're not going there because they're worried that if they put in a sampler, they might introduce bacteria that ride on spaceships, and we know it can survive in space. So they're avoiding that altogether and going for the ancient life in rocks where there's not the possibility of contaminating an existing water body. So yeah, there's great care being taken by, at least by some groups.
Beyond Mars, the next outposts in our solar system to be potential habitats for life are the ice moons of Jupiter and Saturn. Dr. Helen Maynard-Casely has been studying the planetary conditions of these icy worlds in the laboratory.
So as I said, my expertise is sort of recreating those surface and interior conditions of the icy moons in order to sort of understand what the materials are doing and how they interact there. But from the various space missions that we've sent out to Europa and Enceladus, we know, or at least infer quite a lot about their structures. So Europa, everybody gets very excited about because we believe that it has got quite a thick ice crust, or thin or thick, again, we're not entirely sure how much, but there's a global ocean underneath that ice, and that should boundary straight onto a rock mantle, a rock inner core. So at that interface, you've got rock and water, quite warm, like probably more than room temperature, so you've got potential for that water to pluck out minerals, nutrients, and then of course that whole ocean is shielded from the intense radiation of Jupiter. So it's a rather snug little place to be.
So I think, that the community is fascinated by the fact that there's water, known water, and liquid water in these very far-off moons of Jupiter and Saturn. But this gets back to the origin of life, right? So we have life occupying these chemical hot springs down deep in the oceans, and they're some of the most primitive organisms, no doubt. But it gets back to that question of, how do you make something that's as complex of life from very simple building blocks? If you can't do it in the oceans, then I would say you're wasting your time going to Europa and Enceladus, because those deep oceans would never have the wetting drying cycles. So they probably and very likely have the kind of elements we see in the deep oceans on Earth. They may have hot smokers, they may have mineralized water-rock interactions, but from our group's perspective, if you never had an exposed land surface, you probably never got life. And so without that, yeah, we'd really question whether it's worth going.
Perhaps meteors punch through the ice crust to deliver the additional organic chemistry required.
Potentially, yes. I've seen that there's a big change in the craters. So there are craters on the surface of Europa. Let's talk here. The surface of Europa is very young geologically. It's at most 100 million years old, which is why a lot of people get excited about the potential of activity. Craters up to about 30 kilometers are pretty normal. They compare normal for an icy satellite. They compare quite well with the similar sized craters adjusted for gravity on Ganymede and on Callisto. Now, once you get above 30 kilometers, they change very dramatically in morphology. You don't get the sort of big crater, you don't get such the crater shape, you get a sort of ring-like structure. Now, again, the modelling of that is not complete, but you could imagine that that's happened because something's actually punched all the way through, and then water is sort of squidged through, and it would maybe form that. There's a big debate as to how thick or thin the Europa crust is, but I believe that from the cratering record people see, it points to it more being in the 20 kilometres range. That's good because it would definitely protect anybody down there. It's bad because it's very difficult for us to get down there and actually go and find them. So we'll still see. Enceladus, though, which is one of the moons of Saturn, is, I believe, quite a surprise. It's absolutely tiny, and so when Cassini got there and saw these massive geysers coming out, the first big question is, where is all the heat coming from? And it's something that there's potential that it's tidal friction, or is it radiogenic heating? And there's still not a sort of definite, right, it's definitely this, but we know there is a lot of heat coming out of Enceladus. And it is very, very small. And now we know that from Cassini, the way it sort of passed by Enceladus, we know that there is an ocean underneath the South Pole. So again, the other potential's there. But whether that ocean is trapped in ice or actually goes all the way down to the rock, we're not sure yet. So certainly the ingredients seem to be there. I mean, or we infer the ingredients there. If the water, the ocean goes all the way down to that rock crust and you've got water-rock interactions, then there is also the potential that if it's too deep, the pressure of the water can go so high that you actually solidify the water. It becomes solid ice. So Europa's one moon, but it has a much bigger sister, Ganymede. And it was thought that Ganymede would have an internal ocean. In fact, actually, internal oceans are sort of seen as a must-have for most icy moons now. And the reason why people got less excited about Ganymede was thought that the ocean would be so deep that the water would then freeze and isolate everything from the rock, and so you couldn't get these interactions. However, there's been more work that looked at the interactions of the dirty stuff, the potential salt in Ganymede's ocean, and actually it could cause layers, so you could potentially get a solid, liquid, solid, liquid, solid, liquid ocean. And a few of the models worked out that you could get liquid in contact with the rock. So I think there's a lot of justification in doing a lot more study in the potential of taking those ingredients that could be in the bottom of Europa and Ganymede and potentially Callisto, because there's a lot of environments that we think like that in the solar system, and to find out a bit more about how the biology might work down there.
Discovering geysers emanating from the moon, Cassini was retasked to fly through the plumes and make close-up observations.
So they managed to detect, I think, at least CO2 and methane, for instance, but really what they want to look for is the potential of amino acids, the building blocks, proteins. And so that's why there's now a proposal to send another mission there. It's called ELF, or Enceladus Life Finder. They would fly a better, more sensitive mass spectrometer that would be able to directly detect the potential of amino acids. Now, amino acids don't necessarily mean life, and I know that the ELF science team have come up with a sort of cube matrix of observations. Amino acids is just one of those, and there's a number of other things, parameters in that sort of cube. What could they detect for in order to say that there's actually something in there?
Titan, the moon of Saturn, has always drawn attention to itself. A mysterious satellite with a dense and cloudy atmosphere, liquid oceans, rocky terrain, and abundant carbon organics.
So Titan's the first planetary body apart from our own Earth to see liquid on the surface, and that's these big lakes and seas that are ethane and methane, and it's got a very thick atmosphere, much thicker than our own atmosphere. Because of that, it controls the temperature very well on the surface. So globally, around minus 180 degrees C, and it hardly varies from that value. So if you want to study the surface of Titan, from my point of view, it makes it very easy. All I have to do is go drive to 90 Kelvin and just and sit around there. So you've got those conditions, you've got very thick nitrogen, but there's also methane in the atmosphere. Now that methane was always a bit of a mystery. It was actually first discovered by Gerald Kuiper back in 1944. And it got everybody a bit interested because methane shouldn't really be held on to by Titan. It's quite small, doesn't have quite the gravitational field. The methane should have escaped into space. And so automatically there was like, well, where's that methane coming from? That starts to get Titan a little bit more interesting. But then, of course, you've got this methane, you've got this nitrogen, and you've got this atmosphere that isn't well protected, doesn't have a magnetic field like we do on Earth. And so you've got all this cosmic and solar radiation that causes interactions to happen. And you see interactions into bigger organics, things like benzene, acrylonitrile, anything with C, H and N, pretty much. There's a pathway that potentially can form. This bigger stuff starts forming and then starts raining down onto the surface. So you've got this very, whenever you see Titan, it's very orange and hazy, and that's what this organic haze is. And this is thought to have been going on for a very, very long time, so much so that any water ice that's on the surface of Titan has been buried completely, that there's actually just a massive carpet of organic material.
Recently discovered vinyl cyanide, C2H3CN, is an organic molecule which helps form biological membranes in the atmosphere.
These molecules have been recently discovered on Saturn's moon Titan. And this is quite an exciting discovery because these molecules are the building blocks of what's needed for forming the cell membrane. And the cell membrane defines the barrier of a cell, and protects the inside components of a cell from its outside environment so that the cell can metabolize and grow and divide.
It's hypothesized that for the very earliest life forms, there were probably already naturally existing membranes in these hydrothermal vents that the bacteria were basically able to use to partition these chemical processes. And certainly in systems such as Titan, where there are also these membranes available, perhaps this could actually serve as a useful precursor for, again, these self-replicating chemical systems to evolve. It's not the only thing they will require, but it could certainly help and basically have these micro-environments developing for life to develop.
The next possible habitat is the outer reaches of the solar system, a newly visited world showing a complex environment with the potential to harbour microscopic life.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. Not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice. One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. That they're actually forming way out in the solar system where no one really expected.
We know that microbes can continue to have a very low but useful amount of metabolism in extremely cold and extremely dry environments. So, for instance, in these Antarctic soils that we sampled, we were observing that microbes in there could very easily oxidize molecules such as hydrogen at temperatures as low as minus 20 degrees, and these were in incredibly dry soils. So I'd imagine that in certain planets where they have very low temperatures and are very dry, it would be possible, if there is an energy source, for at least a very, very low level of metabolism to occur. And according to all the, basically this comes down to thermodynamics, and with a warmer planet, then as long as it's not too warm, then metabolism will be more favorable, and this will yield much faster evolutionary processes. But certainly in reasonably cold environments, maybe down to minus 80 degrees or so, you can still have microbes survive and do some very, very low level of metabolism to at least tick over, maybe not necessarily grow.
Yeah, so listen, organic molecules are extremely complex. So carbon is one of the most common elements in the universe. And we know that it's on comets. There was that beautiful Rosetta mission that landed and sampled there. But they're very, very simple molecules. And so same with the organic molecules that have been found so far on Mars and the ones that are inferred on Pluto, they're very, very simple. Now, the exciting thing about Pluto is what we didn't know until we got closer up is that it's got a complex history. We can see different domains, and that means there was activity there. And if there's activity, like geological activity, and organic molecules, and a surface, then there's interesting stuff going on. So actually, that looks like an interesting environment. The missing part of that equation in terms of thinking about complex life is the sun is so unbelievably faint at Pluto that you'd never have probably the possibility for photosynthesis, which is what allows oxygen to rise and allows for complex like us and elephants to be around. That's a whole nother step away. So we wouldn't predict, a complex advanced civilization on Pluto, but maybe microbes.